moving the host. I'm just moving the pattern. Got it? Good. All right. So everyone gets brute force. That's all to it. Okay? The time complexity is big O of Mn, where M is the length of the pattern and N is the length of the what? Host, right? Now, a long time ago, three computer scientists, Don Knuth, Morris, and Pratt, they figure, well, we can optimize this naive or brute force algorithm by not naively shifting the pattern by only one position every time. Because if we can determine that, well, if we shift the pattern by one, we know that we aren't going to get a match. There's no point in shifting by one position every time. So you can skip some of the what? Shifts, because you know they wouldn't create a match. So they came up with this algorithm, the KMP string matcher. So I'm not going to discuss the KMP string matching algorithm, but a subroutine of the algorithm is something called the prefix function, aka the failure function, aka the longest prefix proper suffix array. So you use that as a subroutine for the KMP algorithm. So the first part of it, I'm going to show how you compute what? The failure function. Okay? It's a table in your book. So I'm going to erase all of this besides this because I want to reuse this. That was the goal, to reuse this stuff and organize our answer in the same way so we can compare and contrast. But I need all the board space, so how do I do it? Folks will remember this stuff? All right, so I'm going to erase this part of it so we can reuse this stuff, all right? Hope you remember everything else we had. Oh, what's the total number of pairs? Anyone remember? What did we have? 5 what? 16. How many pairs total? 16. Okay, I'll take your word for it. 16 pairs total. 16 pairs. There was 16 pairs total? Yeah. Okay. Yeah. Because I want to compare that with KMP. How do we count for pairs? Adding all this stuff. Everything I had in this column. But I've erased it. All right? All right. I think I'll have this in a lecture handout. That's why I want to use this as an example. Okay. So how do we determine what is called a failure function? So the way KMP works, you compute something called the failure function of the pattern, not of the host. The failure function of the pattern. The failure function of the pattern is exactly the same as computing the longest prefix that is a proper suffix of the pattern. So we compute an array, at times it's called the LPS array, the longest prefix that is a proper suffix. So I'm going to go manually how you do it so you can conceptually understand what's happening. Now I'll go through how the algorithm works so we can get an amortized linear time, all right? But first I just want to go through it so you understand how it works without knowing how the algorithm actually does it in linear time. All right. So we want to compute the failure function of the pattern, pi of p. It's an array, basically. What's the length of the pattern? What's the length of the pattern? 5. So I have 5 entries in the array. 1, 2, 3, 4, 5. I want to compute each of these things. So first, I consider the first prefix of my pattern. My first prefix of the pattern is what? Just what? A, right? Can I find a prefix of A that is a proper suffix? A proper suffix is one that does not cover the entire string. Can I find a prefix of A that is a proper suffix of A? No, because I will have to use the entire string, right? So the longest prefix, the what? Failure function gives you the longest prefix that is also a proper suffix of the string. So pi of the first substring is the first prefix is always 0. That's a freebie. Okay. Now I'm going to consider what? The prefix of length what? We just considered the prefix of length 1. Now I'm going to consider the prefix of length what? What's the prefix of length 2 of the pattern? We're going for the shortest prefix or the prefix? I did 1 already. This is a prefix of length 1. What's the next prefix? of length what? 2. What is this? What is that prefix? AA. Good. I'm just going here, there, there. These are the prefixes. Everyone gets that? AA. So, what's the longest prefix that is a proper suffix of AA? Can I get a suffix of length 1 that's also what? A prefix? Yes. Because this A is a prefix and the suffix is A. That matches, right? So that's 1. Can I get a prefix of length 2 that is a proper suffix? I just explained that like a minute ago. Huh? Can I get a prefix of length 2 that is a proper suffix of length 2? No, because then I'll consume the entire string. Proper means you cannot take the entire string. Everyone gets that? So my question is, what is the length of the longest prefix that is a proper suffix of this string? 1. Okay. Now, we're going to now go to the prefix of length what? 3. Everyone gets that? Which is what? AAB. Can I get a prefix of length 1 that is a proper suffix of length 1? No, because this A and B do not match. What's about length 2? AA and what? AB. No. And I cannot consider 3 because it wouldn't be proper. Everyone gets that? So let me see if you catch it. What's the longest prefix that's a proper suffix of that string? 0. Because we didn't find any. All right. So this is 0. Now, what's the next prefix we're going to consider? AA what? BA. So we want to find the longest. Can I find a prefix of a suffix of length, a proper suffix of length 1 that is also a prefix?
Yes.
Yep.
Yes. A and A match. What's about 2? No. What's about 3? No. 4 is not a possibility. So the longest prefix that's a proper suffix of that string is what? 1. Everyone gets that so far? Now, what's the next thing we're going to consider is what? AA and AA. Everyone gets that? What's the longest prefix that's a proper suffix? 2, right? Can I get longer than 2?
No.
BAA, no. And AA, no. We wouldn't get. This would be what? AA, this suffix would be AABA. But we don't have AA. Do we have AABA? ABAA. But we don't have AB. So we cannot have something of length what? 4. The longest we can get is of length what? Huh? I took 2, right? So this function is called a failure function. You see how we use that. I just want you to understand how you compute a failure function. So if I give you a pattern, I say compute a failure function of the pattern. It's just an array that represents what? The longest prefix that is what? A proper suffix of every possible prefix of what? The pattern. Everyone gets that conceptually? Now, we just did it manually, but let's see how we actually do that in code so we can achieve linear time. Yes?
We were looking for a prefix on the suffix.
What's that?
When we were looking for a prefix that could also be a suffix, were we looking at the top string or the lower one?
The beginning is the prefix.
I'm
So-
still saying that are we talking about the one which is below?
Oh,
Or
the pattern, that's the pattern, the one below. P, the pattern. This one.
Okay.
Pi of P. Okay? You compute the failure function of the pattern, not the host. And you see why we do that. Yes?
Can you explain what you mean by proper again?
Proper means you don't use all the characters in the pattern. Okay? Like a proper subset doesn't include all the elements of a set. Okay? I cannot consider the entire string, then it's no longer a proper substring. It's just a substring but not proper because it's equal to the string itself. Okay? Now, let's see how this works in code. So I'm going to go through quickly because we need to speed up. KMP is the most important algorithm. So I'm going to go through this to show how this is computed in code. A, B, A. So this is how it's done. Then I'll make the argument Y. It gives you amortized linear time. All right? So I have this array that I want to fill. I know the first entry of the failure function is always going to be what? 0. So this is 0. I'm going to use 2 indices. This is my J index and this is my I index. What's the idea behind this move? Well, if I find what? A prefix as a suffix. The question is, can I extend it by one more character? if I can, then I move I and j and increment the length by 1. Right? Everyone agrees? So for example, if I have A, right? I know we have a match here, right? So far the longest prefix as a suffix is 1. But since if I advance I and advance j, I still have a match. That means I can increase that length by what? 1, right? If I keep having matches, I can always extend the length of the longest prefix that I can find. So let's do this quickly. So currently I know the length of the longest prefix as a suffix is 0. So I start from here. Does the ith and jth character do the ith and jth characters match?
Yes.
That means the previous longest prefix as a suffix can be extended by what? 1. So I make this 1, and I advance both I and j. So I advance j, I advance I. So this tells me the longest prefix as a proper suffix of the prefix 2 is 1. All right, because we had a match. But can I increase it and make it 2? Do the ith and jth character match? No, that means I cannot extend this longest that I knew before as 1 to what? 2. Everyone agrees with that? I cannot extend it. Now, so if I cannot extend it, this is a strategy that Knuth was thinking about. Then I want to go back in time to the previous longest that I knew and see whether I could extend that. If I can, I'm going to go back in time again until I find what? One of the previous longest that I can extend. If I cannot do that until I get back to the beginning, then I know, oh, there's no prefix as a suffix, so I'm just going to advance j. And that's the idea behind it. So I'm going to go through manually, so you see how that works. Now, we wanted to see whether we could extend 1 and make it what? 2. But we had a mismatch. So what was the previous longest prefix that was a suffix prior to the time we found a mismatch that we couldn't extend? It was what? 0, because the first character was 0. Right? We wanted to see whether we could extend the 1 to 2, but we couldn't. So we went back in time and said, prior to that longest string that we had was 1, what was the longest we had before, which was what? 0. So you update j to what? Pi of j minus 1, which is what? Before we had this mismatch, which was 0. So I bring j back to what? Position 0. So I say, I know I can extend 1, but the previous longest I had was 0. So I'm going to go back in time. Now, I went back in time. Do the ith and jth character match? No. So that means I cannot extend this 0 and increase it by 1 because I had a mismatch on the what? First position. Everyone gets that? Now, obviously, if I had a mismatch on the first position, I can't go back any further, right? So the only choice I have is to advance I. This becomes 0 because I couldn't match it at all, and I advance I. So if you keep going back in time until you get to the beginning of the string and you have a mismatch, you can't go back in a negative position. So you advance what? J and make that 0. Now, so we've advanced I. Do I have a match?
Yes.
Yes. The ith and jth character match. That means this value, which was the longest we had before we attempted to make that match, can be increased by what? 1. So this becomes 1. Anytime you have a match, you try to advance I and j to see whether you can increase the length. Everyone gets that? So I advance j to this position, and I to this position. Do I have a match? Huh? That means the previous longest prefix that we knew can be extended by 1. This becomes what? Which is exactly what we did by just mindlessly doing it while thinking about it before. Okay? Yes?
I noticed that after the first one, the first time that 0 occurred, we moved both of them 1, right?
Mhm.
Both I and j. How come is it that after the middle 0, you kept j in its place, but you moved I forward without j?
I know I can't have a proper prefix in this stuff. So j start from here, I start from here. This was 0 because we couldn't, previous longest thing we knew. But we have a match, the ith and jth characters match. So I take the longest we knew and increase it by 1. So this is 1. Anytime you have a match, you want to see whether you can extend it further. So you advance what? Both j and what? I. Everyone gets that so far? But now we have a mismatch because the ith and jth characters do not match. What does that mean? I cannot extend this 1 to what? 2. So since I couldn't extend this 1, I'm going to go back in time. The way you update j will be equals to pi of j minus 1. I'm going to go back to the previous longest prefix that I computed before, which will be what? 0, because pi of j minus 1 will be 0. So I move j back to this position. That's the previous longest that I had. Okay? Then I say, well, do I have a match now? Do I have a match? Do the i's and j's character match? Not a trick question. No. But can I go back in time? Can I move j further back?
No.
No. So I know that, well, there's no prefix that will match this b, so I put a 0 here. And once I do that, I advance I to the next position. Okay? So that's how it works. Do I have a match here now? So I go back to the previous longest that I knew and add 1 because we just matched it. So anytime you have a match, you advance both what? J and what? I. Do I have a match? What will a match mean? The previous longest we had has been increased by what? 1. That's it. That's all to the Fourier function. Now, you're wondering, why can't I just do something like a nested loop? We want to do this efficiently. So it turns out that you can compute the Fourier function in linear time. Actually, the technical term for it is amortized linear time. So I'm going to make the argument, sort of hand-waving argument. You see this index I. I never backtrack with I always move I what? Ahead. Everyone notice that? I may get stuck at a position, but I never move I what? Backwards. Everyone agrees with that? So if the length of the pattern is what? M, then I will advance at most what? M. Okay, it could get stuck at a position, but typically maybe 1 or 2 times will be a constant number of times. So I know moving I across this will be at most something of order what? M, right? Now let's look at J. J is the tricky argument to make, which we're going to do hand waving. Now, J is a bit tricky because I can move J forward and what? Backwards. Everyone saw that move in the first string we did. We moved J forward at times, we move it what? Backwards at times. So how do we know that J will give us on average M moves as well? It's easy to make the argument because we're just going forward. But J is trickier because we're going backwards and what? Forward. So I'm gonna state without proof so far that J is also going to take us what? Big O of M. So this whole thing is going to be big O of what? 2M, which is big O of M. So to compute the Fourier function is what? Linear in terms of what? The length of the what? Pattern. Okay, now. Why am I also concluding it will take J at most M moves? Well, here's the idea. If I have a bank account and I deposit and withdraw, I expect to have an amount that is linear because anytime I what? Do a deposit, I compensate by doing what? A withdrawal. So on average, I expect my balance to be hovering around some value. Everyone follows that argument? So if I'm only making what? Deposit, then my amount will be growing. If I'm only doing withdrawal, I'll get to 0. But anytime I withdraw, I do deposit, withdraw, do deposit. I can argue that on average, my balance will be hovering around the same amount. So the way you prove that formally, which is above the pay grade of this class, we have something called the Banker's method. And there's something you use in physics called the potential method to argue that if I'm doing withdrawal and deposit, I can argue that I will have a constant move on average. So it's called amortized time complexity. So on average, we expect that what? J will also make what? Something of order M moves, right? Because every time J goes backwards by a certain number of units, we compensate by skipping and going forward, backwards, forward. So on average, we expect that to be constant time. So, everyone guess that? How are we doing on time yet? What's the time?
9:40.
40?
Yep, 9:40.
Okay. So I think I can do one more example. I'm going to go through one example quickly. 10, 111, 010. What did I say? Huh? 101? 10 or 01? 010?
11.
010, yes. Oh, 10, 111, 010. 010. So let me use what I have in my notes. Okay, I'm going to compute a failure function. All right. So I'm going to go through this quickly. What's the length of the array, the LPS array? 3, 6, 8. Everyone guess that so far? This is always 0, the first entry. So J starts here, I starts here. Do I have a match?
No.
Since I have a mismatch on the first character, this becomes 0 at advance I. Do I have a match?
Yes.
If I have a match, the previous longest we had was what? So I make this 1 in advance what? Both what? I and J. Everyone remembers? J goes here and I goes here. Do I have a match?
No.
So where do I move J backwards to?
What?
So the previous J value was 0. So I move it back to index 0. Everyone guess that? So J goes back here. Do I have a match?
Yes. Yes.
So we do have a match. Everyone guess that? Everyone guess that? So my previous is this 0. Plus 1 is what? 1. Okay? Now, because I had a match, I want to see where I can extend that by what? 1. So I advance both what? I and what? J. Do I have a match? No. So what's the pi value prior to the mismatch? This would be what? 0. So I move J back to index 0. Do I have a match?
Yes.
Yes. So this is the current maximum we have when we went back in time, plus the match we just had, which makes this what? 1. Everyone gets that so far? Now, because I had a match, what do? I want to see whether you remember the algorithm.
Advance I
I and J. So J goes here, I goes here. Do I have a match?
Yes.
Yes. So 1, right? We just had a match. So 1 plus the 1 will give you what? 2. So you advance it further to see if you can still have a match. J goes here, I goes here. Do I have a match?
Yes.
So we make this what? 3, advance this, J, advance this, I. But this is what? A mismatch, right? So what do? I go to position this, which was what? At what?
3.
This was at index 4. Okay, so we had this. So I go here. This is what?
1.
1. So I go all the way to index 1. This is what? J. Now, do I have a match? Yes. So since I have a match, I'm going to go with what? 2. Index what? 2. All right. So I went back in time. I said, well, I couldn't extend this 101 to make it 4, but my previous thing was 1, so I went back to index 1 because this was 1. I had a match here, and I could extend it because it matches this, so this becomes 2. Someone get that argument I'm making? That's going back in time. Basically, the update to J is pi of J minus 1. Whenever you have a mismatch, you keep going back. If you have a mismatch at the beginning at index 0, then all you do is what? Just advance J and set that to 0 because you couldn't possibly match it. All right. So let me speed up. I'll come back to this if folks still have questions on KMP. But I want to finish KMP quickly because it will take us more time. All right. So I'm going to erase all this all of this here. Yes.
Just to be clear, when we have that 2 at the end, the prefix and suffix that we're representing is the 1 and the 0 at the beginning?
Okay. So when we went back, what's the thing? We had a mismatch at this point, right? I think it was here we had a mismatch. So I went here, said, well, index 3, right? At index 3, 0, 1, index 2, 0, 1, 2. This was a what? 1. And we could extend that 1 by 1. That's how we get into 2.
Okay.
Right? And the way you update is j equals what? Pi of j minus 1 to go back in time. If I still had a mismatch, what would I do? I go back again, j equals what? Pi j minus 1. But what if I have a mismatch on index 0? Who can tell us what we do if I have a mismatch on index 0? You just advance j and set that value to 0 because you couldn't possibly match it. Okay? So I have the pseudocode on the handout. You can go back and read it. If we have time, once I'm done with KMP, I'll do one more example. I'd like to get to KMP. So what's the stuff we just had for this thing? Was what? 0 what? The failure function was 0, 1, 0, 1, 2?
Yes.
Okay. Let me write that down so I don't forget. Pi of p equals what? 0, 1, 0, 1, 2. Someone asked this question. I probably should emphasize this. The failure function is the failure function of the pattern, not the host. Everyone? The host is the longest string. So let's go back now and do this stuff. All right. Remember, in a naive algorithm, you always shift by what? 1 position every time, right? Okay. So we'll be doing exactly the same thing. We'll do what? We have a match, and then we have a mismatch. How many pairs did we compare so far? We are doing KMP algorithm now. Okay? 5 pairs, but we have a mismatch. Green? Now. But instead of shifting by 1 position, I'm going to take advantage of that failure function we just calculated. Let's see the way I take advantage of that. I know that I had a match up to this point. Let me remove this stuff from here. Everyone agreed that everything matched up to the time we went to the B. That's when we had the mismatch. Everyone agrees? Now, how do I know how much should I shift the pattern? Well, the question then is, what if I shift this by 1 position? I'm just going to shift it by 1 position. Notice we'll have what? A, B, A. Everyone agrees if I shift it by 1 position, that's what I'm going to have? Now, notice this part of the string is the prefix, and this part is a suffix. How do I know these 2 things wouldn't match? When I shift, this becomes the prefix, and this part becomes the suffix of what? AABA. It's the same AABA. So the only way that shift is going to make sense if the prefix matches what?
The suffix.
The suffix. How do I know they wouldn't match? Well, for a character of line 4, 1, 2, 3, 4, the longest prefix as a suffix is not 3, it's what? 1. So I know they wouldn't match if I slide it by only 1. So there's no point in doing that. Okay? Let me see where you follow the argument. Can I shift it by 2? Will it make sense to have a shift of 2? Why not? Let me do it again so you fully understand. If I shift it by 2, I'm going to have A, B, A. But by doing that, what I'm saying is the longest prefix that is a suffix of AABA is 2. But is that 2? 1, 2, 3, 4. It's 1. So I know I'm not going to have a match. There's no point in shifting by what? 2. Right? Now let's see what shift will make sense. So I'm going to speed up through this stuff. Right. Okay, so let's look at it. What's the longest prefix that's a suffix in this stuff? 1. Since the longest prefix that's a suffix is 1, that means I'm going to slide this at this position. A what? What the original was A what? B A. Notice this matches that. Okay? I'm going to tell you the significance of that 1. The 1 says that's the number of characters in a pattern you can skip. You don't really need to compare because you know they're going to match. Since my failure function gave me 1, I must now begin matching the mismatched character with what? The second character of the pattern. Anyone guess the reasoning behind that? The 1 tells me the maximum number of characters that will match from the prefix is what? 1. I know these 2 already match. So I only need to begin attempting the match from what? A second character in the pattern and the mismatched character. If you got that, that's the algorithm. I'm just going to keep doing the same thing over and over. Everyone got the reasoning why I'm shifting it all the way to this position? Because what? This is how many characters prior to the mismatch was what? 4. 1, 2, 3, 4. So what's the longest prefix that was a suffix prior to the mismatch? 1. That tells me I can shift as many positions as I want, but only one character will match. So I know only this A will match that A. So I begin the comparison from what? The second character, because since I'm skipping only one character, this tells you how many characters to skip. Basically, that's what it tells you. Right? So I can skip the first character in the what? Pattern. That means I must begin attempting to match what? The second character of the pattern with the mismatched character in what? The host. Everyone gets that? So, I'm going to now move quickly. Since we have what? A, what? B, A, what?
A, B.
Oh, I should have what? B, A, and another what?
A, B.
B. Is that right? This is the host? Is that the host?
Yes.
Okay. Now, this is where we had a mismatch at this position. Since I want to begin comparing what? The second character of the pattern, where should I shift the pattern so I can compare the second character of this pattern with the mismatched character? It's kind of difficult. At what index? This is index 0, 1, 2. Where should I shift the pattern so I can begin comparing what the second character of the pattern with the mismatched character in the host?
Index 3.
3. 0, 1, 2, 3. So this would be A, what? A, right? So what is my shift? My shift is what? 0, 1, 2, 3. Everyone, guess how you determine the shift? Let me see. I hope this is obvious. But why I'm not adding additional characters to the pattern? Who can tell us why I'm not adding additional characters? We had a mismatch, so there's no point. We can't go beyond a mismatch. So I know we still have a mismatch here. Okay? So the first shift is 3. Is that a valid shift? No, because we didn't find a match, right? Everyone gets that? So let's determine how we find the next what? Shift. So I look at the substring prior to the mismatch is only what? This portion, right? What's the pi value of that prefix that has only one character? 0. That tells me when I shift, I cannot skip any character in the what? Pattern. Remember the 1 said we could skip the first character. Now 0 tells us I'm not going to skip anything. Okay? So that means this A, the first character has to be paired with the what? Mismatched character because I'm not skipping anything. So the next thing will be A, B, A, B, A, B, A. Then we'll have what? Since I'm not skipping anything, this A has to be paired with this. Still I have a mismatch. Because A doesn't match with that, right? Now let's finish the table. After my first shift, how many pairs of characters did I compare? I hope that's pretty obvious. This is the first shift to compare 5. The second, how many pairs? 2. During the third, how many pairs? 1. Good. Okay. Now, if I have a mismatch on the first character in the what? Pattern, right? I can go to a negative what? Position, right? So all you do is just slide the pattern by 1 position because there's no way you can match it at that position. So if the mismatch occurs on the first character in the pattern, slide the pattern by what? 1 position. It becomes like what? Brute force. You can't optimize it any further if you have a mismatch on the first character. Everyone gets that? So now we have a mismatch here. What's the index we went to? 0, 1, 2, 3, what? 4, and we did 1 pair. So our next move will be to go to what? Index what? 5. Index 5. And since we had a mismatch here, you can no longer match this here. So slide it to index 5. A, B, A, B, A, B, A. Let me see if I can pronounce that word. A, ba, ba. Something like a baby talk or something like that. All right. Like we're in nursery school. All right. Anyway, everyone gets it so far? 0, 1, 2, 3, 4. Now we can no longer match this because the mismatch occurs in the first. So you slide it by what?
1.
1 position. So this becomes what?
A.
A, we have a match.
Yes.
A, we have a match. B, we have a match. A we have a match, and A we have a match. So we found a valid what? Shift. Everyone gets that? How many pairs did we compare?
5.
5. Now, what's the total number of pairs? 13, which is better than what? 16, assuming that all the energy we put into calculating what the failure function didn't really matter, was negligible. Typically in the real world, your host string is considerably longer than what? The pattern. So you can just ignore the time put into computing what? The failure function. It will be pretty negligible. Okay? Yes?
So whichever one it fails on is, so say like in the last.
When you have a mismatch, the character you have a mismatch in the host, you can never move backwards in the host. So the goal is to keep shifting what? The pattern, but you don't want to blindly shift by only one index every time. The failure function tells you how many characters in the pattern can you skip. So if you look in the value for that pi function, it tells you 2. That means you must begin attempting to match what? The third character in the pattern with the mismatched character. It tells you how many characters from the pattern you can skip. Okay? Let me do one more example. All right? So I'm going to go back. How are we doing on time here? I lost
20
my watch for
minutes.
some reason. I don't know why I did that, but
20 minutes.
20 more minutes. I think we can do both of these things. So hopefully you folks can remember this stuff. I have 10111 011. 10111 011. What's that? What was it again? All right, I think I should bring my notebook here
Oh.
to see it myself going up and down.
What?
I wrote the example in my notebook. 10111 10111 what?
Oh.
010. I'm going to compute the failure function for that, all right? So, what's the length of this thing? 8?
Didn't we just do that?
Is it the same thing we did?
I thought we did the failure
Yeah, 0,
function.
0, 1, 1,
Oh.
2, 3, 2.
We did that.
Okay, so let me go to another example. What is it? 10111 011. How's it different? Oh, it ends with 11. 11. Okay? Now I'm going to compute this stuff. 1, 2, 1, 2, 1, 2, 4. Do we have all of this? What will be the first entry?
0.
0. Begin I, J, and I. Do we have a match? No. But since the mismatch occurs at the beginning, I can't go backwards, and so this becomes 0. What do I do if the mismatch occurs at the beginning?
Move both forward.
Just advance what? I. This is not KMP, I'm just calculating the what? The failure function. So I goes here. Do I have a match?
Yes.
Yes. Since I had a match, that means the previous longest thing we have can be increased by what? 1. So this is now 1. I advance what? Both what? J and what? I. Now, do I have a match? No. Since I don't have a match, I cannot extend this by what? 1. So what do I do? Well, I'm going to go back in time to what? J will be reset to J minus 1, which is what? 0. So J goes back to this. Do I have a match? So the previous longest we knew at position J was what? 0. And I add 1 because we just had a match. This becomes what? 1. And because I had a match, what do I do? Advance both what? J and what? I. Do I have a match? No. So I go back in time to the previous, which is 0. I go back to position 0. Do I have a match? So what do I do? The 0 can be extended by 1. So this becomes 1. And since I had a match, I advance both what? J and what? I. Everyone gets that so far? Do I have a match? Yes. Since I have a match, the previous longest we had can be increased by 1, which is now what? 2. Advance both what? J and advance what? Alright. Do I have a match?
Yes.
Huh?
Yes.
So the previous longest we knew can be increased by 1, 3. Advance what? J. And advance what? I. Do I have a match?
Yes.
So the previous longest we knew can be increased by 1, 4. So that's a prefix function. The failure function, prefix function, LPS array, same stuff. All right. So let me do one example quickly. One more example on this stuff. I probably just need to make up that example. Now, at times on the exam, when I give this stuff, I will tell students to highlight all the pairs of characters in the host, and because you wouldn't be able to draw something like this on the exam if I asked this. So all you need to do is just maybe boldface or make this in red. Everyone can change colors in like a word or something like that. You just highlight and then go to the color thing and select the color you want. So we can show the actual characters being compared, right? Because you wouldn't be able to draw boxes around stuff, all right? So be able to finish a table like this. The shift index, what? Highlight the pairs of characters that are compared in the host and pattern, then give the number of pairs in this column. You should be able to fill in a table like that, all right? So I'm going to go over one more example. Now, I'm going to erase this quickly, and let's do one last example. Trace the action of KMP for this string 10101, and let's say this is 11010 101 let me see. Let's see what 10101. 1010. Let's see. 10101. Yes. So this is a good example. Now let's just do by hand waving. What's the pi function of this? Is our pattern P. This is our host. What is pi of P? Instead of going through all the steps, let's just do by hand waving. 1, 2, 3. What's its value for this function? The pi value? 0. Second one is also what? 0. Third one is what? Fourth one is what? 2. Next one is what? 3. Okay? Now convince yourself that is the case. Now I'm going to do what? Apply KMP. Now we're done with the failure function. So our first shift is index 0. We have what? 1 and 1. 1 and 1 match. 1 1 what? Someone will read the host to be 1 1 what?
110100101011.
1101
00
00
10.
10101.
Yes.
Okay. And our pattern is what? 1 0. So we have a mismatch here. Someone guess that? How many pairs? We compared.
2.
2. So whenever we have a mismatch, we compute the pi value of the substring prior to the mismatch. So we want to compute the pi value for up to this point. What's the pi value for only the substring that consists of 1?
0.
0. That means we aren't going to skip any character in the pattern when we shift. Someone guess that? So the next move will be, I'm going to attempt to match what? 1 1 0 1 0 0 1 0 1 0 1. Since this 1 0, I'm not going to skip anything. This is a character that we had a mismatch. I must begin matching the pattern 1 beginning at this position because I don't skip anything. Everyone guess that? So we have 1. Do we still have a match here?
Yes.
Do we have a match?
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 No.
So our mismatch is now at this position. And what was our shift? And what index did we shift the pattern? 1. How many pairs of characters did we compare? 5. Okay? Now, we had a mismatch at index index 5, right? Who can tell us in my next shift how many characters will I need to skip in a pattern? This is what? We had a match up to this point. So the longest prefix that was the suffix is what? 2. That means when I shift, I will begin attempting to compare what the third character of the pattern with the mismatched character. Everyone gets that? So should be pretty obvious. Now let's go to this. So when I shift 1 1 what? asterisk is the mismatch character 10101. Now I must begin comparing with the third character of the pattern, which is what? 0, right? So that'll give us what? 1, 1. We already know these two are going to what? Match. Because this 2 tells us these characters are going to match 2 characters, so I begin comparing from the what? The third. We skip those 2. Now, do I have a match? A mismatch. Let's see. What's my shift index?
3.
3. How many pairs of characters were compared after during this shift?
3.
How many pairs?
3.
1, because we skipped those 2. That's the whole point going to the, because we know they're going to match, so we skip them. So we begin comparing from what? The third. This tells you how many characters from the pattern you skip. So we don't actually compare those 2 because we know they're going to match. Question, how do we know those are going to match? Because I know when I slide this, the longest prefix as a suffix is 2. So I know these 2 will match these 2. There's no point in comparing them. That's the whole point in doing the what? Prefix function. Okay? So we compare only what? 1 pair. It was good that I did this second example actually, because I see that people are getting confused. Now, so since I have a mismatch, what's the longest prefix as a suffix of the substring prior to the mismatch? 0, okay. The 0 tells me that I'm not going to skip what? Any character. That means we have 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1. So this pattern, which is 1 at start, I'm not skipping anything. 1, do I have a match? What's my shift index? What's my shift index? 0, 1, 2, 3, 4, 5. It's 5? How many pairs of characters did I compare? 1. Now, let me see whether you remember this. If the mismatch occurs on the first character, what do I do? Just slide the pattern by 1. It becomes like naive. So now we will have a shift index of 6, 1, 1, 0, 1, 0, 0, and we had a 1 here. This is what we're trying to match now. 1, 0, 1, 0, 1. So I'm beginning from here. 1, do I have a match?
Yes.
0, do I have a match?
Yes.
1, do I have a match? 0, do I have a match? 1, do I have a match?
Yes.
So how many pairs were compared? This is a valid shift. 5 pairs. What's the total on that? Not 15 or 14? 14. Now, how are we doing on time? Time management.
About 11 minutes.
10 minutes? Oh, that's good. Now, what I'd like us to do, let's do the same problem using brute force and then compare the 2. All right? Yes?
Why is on shift 3 there's only
What's that? The third, this one? Huh?
why is there only 1
Okay. How did we go from here to there? All right? I know we had 4 characters matching before we had a mismatch. Everyone sees 1, 2, 3, 4? So I go in here and do what? 0, 1, 2, 3, 4. That's 2. That tells me I need to skip the first 2 characters in the pattern because I know they're going to match. So I will begin comparing the mismatch character with what? The third character in the pattern. What's the third character in the pattern? 1. Because I'm skipping these 2. So I slide this until I get the third character in the pattern to align with the mismatch character. Everyone understands the logic of that? Now, probably the most substantial question is, why am I skipping the first 2? Well, this is the same string. So I know that when I slide this away, essentially what I have, the prefix of this will align with the suffix of itself because that's the same character. And I know the longest prefix as a suffix is 2. That means if I slide this over all the way here, I know these 2, the first 2 are going to match the what? Last 2. That's why I don't need to compare them. Everyone gets the logic of this stuff? Now let's do quickly, since we have more time, I'm going to go to what? Brute force, and we're going to compare. Assuming that what the time it takes